we are going for the harder problems. So, Mr. Jack, I think we roughly went through the simple problem, which is the same one from the blog post he has on his blog, with a bit of a different concept for a mixer. And I think it's labeled simple because it basically optimizes for one variable. And I think the harder one is going to optimize for two variables, which I'm curious to know how is Jack going to approach that. And I'm hoping that will maybe help me click a couple of things together. I don't know, let's see. So anyways, we've solved a very simple problem, something complex like a question involving two variables. We can implement that as well, but this time we'll have to use two optical modes instead of one. So we got two optical modes. Okay, it's not that we're measuring position and momentum of one, because that would not make sense, or that would be actually stupid, because you would basically have certainty and you would not be able to measure both things accurately, I guess, or with certainty. Let's try to minimize the function given by. Okay, so that's now the function we got. As the far more complex functions, go, this one is fairly simple and symmetric in terms of its minimum. We can put this in the form of our unitary. Okay, so here we're just going straight ahead. So that's the function, and basically we're going ahead and using that expression. And so basically, Jack transforms that into, since his opposition operators all commute, we can write this unitary as a series of exponentials, which we can translate to photonic gates. So you basically got that thing, and then you doing all of the necessary algebra, we find that we can represent this series of unitaries as the following photonic gates. Now that gets interesting because there is a control Z gate I see here. Which kind of makes sense because it expresses relationship between the X and the Y, right? Now the question here is, would it be possible to do something like that without a controlled operation at some point? Wouldn't that mean that then this is not a function of two variables, unless that would just be a completely random function? You know what I mean? Like, a function always defines a kind of correlation, right? It correlates the inputs with the outputs, and so that makes that implicit relationship between the X and the Y in this case. So interesting. I'm missing again sort of the what's the intuition rather than like what's the math, right? Because this is literally we take that as a given and then we just go down and say, okay, that translates to those types of gates. But even things like what just came to my mind, right, was, to just say that this makes sense because or the fact that there's a gate that a controlled Z gate or a controlled gate that acts on the both modes. It intuitively makes sense because you gotta be relating them somehow. And then doing all the necessary algebra. P gate control Z Z P Z, and then the mixer. So that's the mixer. Next, let's code this into our pre-existing simulation. We'll try both the previous mixes in our simulation. Let's start with the kinetic mixer again, giving us a final unitary of this. Without further delay, let's code up our simulation. We have a new classical cost function that we have to implement first. In addition, we have defined the value of Planck's constant. Okay, so now we've got our function, it's a different one. Now we have to define the new cost unitary, which we'll be using in the QAOA procedure. We'll have to define the new cost unitary, which we'll be using in the QAOA procedure. This is fairly simple to do, as we have already come out with a gate sequence that gives us our desired gate. Z gate, P gate, Z gate, P gate, control Z gate. Okay. Isn't that in the wrong order, or is it missing something? Isn't this P, like, shouldn't it be ZPZ, control ZP? ZPZ, control ZP, Jack. I think those two things should be, if you've written that well, those two should be, I think. I think. Assuming that's correct, of course. Yeah. We also implement the kinetic mixer for 2 modes. Defining the mixer unitary used in the KO process. Again, that is still okay. So that is still magic for me. What is the kinetic mixer, and how does this? Maybe I should then. I guess at some point. So I guess my next. Let me go for a second. To the top. What are the other points in here? So we've got the simple problem, harder problem, not so grand finale, a quartic function with 2 global minima, another small tangent, higher order gate decomposition, last detour, numerically calculating the cost Hamiltonian expectation value, conclusion. What is this about? Seems like small. Okay. Yeah, those are small things. Let's go. Okay, so let's finish this up first. Where was I? Here. Just so, but yeah. So this runs like before. Will be the squeezing parameter, the circuit depth, and the cutoff dimension. Got a bit of different squeezing parameter here. Circuit depth 3. Once again, like we did before, we'll define 2 functions that run our circuit. One that returns numerical data for the visualization, and another one that samples the circuit again. We'll optimize over only one parameter. What? Okay, so it's just one parameter. P. No. Yeah. It seems like. Yeah, okay, so we're only optimizing over one parameter. Okay. The rest is the one for the mixer. Now our filtrations, we have objective function. Then we choose our optimizer once again. Finally, we can construct our visualizations just as we did before. This time we'll examine a contour plot showing the probability of measuring a specific point x and y, as well as the quadrature showing the probability densities for the individual modes. It is important to note that the contour plot is not exact. Since we passed the modes through a controlled phase gate, they are no longer independent. And thus the probability of a particular measurement can be determined by simply multiplying the individual probabilities of measurement. However, so they are entangled, sort of, right? So this is entanglement again, kind of, I guess. However, we can still get a decent approximation from the contour plot, so it is useful to examine as well. Contour plot defines the probability graph for the first mode, for the second mode, blah 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 blah, all the parameters. So that's the contour plot. and those are the separate Q modes. The blue dot on the contour graph corresponds to the optimal point. I really feel like I'm cheating with respect to this implementation, as I went through many different values of the parameters, like squeezing, cutoff dimension, and circuit depth to find the solution, which is really good. For the most part, this example, when I ran it locally, was super volatile and didn't work a lot of the time. I think it would be interesting to see an extension of this algorithm where not only the unitaries are parameterized, but also the other parameters like the squeezing parameter, cutoff dimensions, and circuit depth. I would also hope that the algorithm performs better and more consistently when we're able to choose our initial parameters with an actual strategy rather than blinding picking some arbitrary set of numbers. Let's try another example, but this time let's be a bit harder on ourselves and actually sample the function to obtain the optimal value, as one is supposed to do with an optimization algorithm. Consider the function given okay, is that another example? That's the function. To match this, so this function, since the distance between the optimal values x and y is larger, we will set Planck's constant to 1 to achieve larger variance. That's interesting, without applying ridiculous amounts of squeezing, which can also mess up the simulation. By this point, you pretty much get the idea of how we implement this algorithm, so I won't go through all of it. Note that I'm only redefining the things that change, the rest will stay the same for the previous example. Okay, so Planck's constant here. What's Planck's constant? And in strawberry fields, Xanadu. That is the quantum of electromagnetic action which relates the energy carried by a photon to its frequency. Okay. So that actually regulates the frequency of the photon waves, I guess. So you can tweak that. Larger variance without applying ridiculous amounts of squeezing. Okay. Which can also mess up the simulation. By this point, you pretty much get the idea. Yeah, okay, so that we went through all that. So he's just changing the function here, optimize, and then the cost Hamiltonian is the same, the mixed ham is the same. H has changed though, right? H bar is 2. Jack. If you say you're gonna change H bar, then change it. Because you haven't. You said H bar 1. Here. So shots 15, defining the function that simulates the circuit. The simulates the circuit returns blah 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 blah. What was that? Yeah, sampling the objective function. Cost. Okay, so you minimize that. More or less, yeah. Define the Y array for the first mode, define the Y array for the second mode. Contour plot that gives the final probability density function. Mesh grid, I don't know how this is working. So it's not awful, but it isn't amazing either. Okay. Even so, I still feel like I'm cheating because I'm still being super selective with the parameters. In addition, this implementation uses a new approach to applying the parameters, where two parameters are optimized and applied to the circuit in both the mix and cost unitaries, and even an odd number iterations respectively. The algorithm does appear to favor a region fairly close to our optimal value, however there is a lot of variance due to the setting the Planck's constant to 2. The not to 2, so, but then you say 1 up there, so you gotta fix that up probably. The not so grand finale, a quartic function with two global minima. Now for the grand finale, we will attempt to apply CVQA to the optimization of a quartic function. However, before we do this, we need to take a bit of a detour to discuss how the heck we're actually going to create a quartic phase gate. What is quartic? What is a quartic function? Every day we learn new things. What is a quartic function? An algebra quartic function is a function in the form where a is non-zero, which is defined by the polynomial degree. Okay, it's a function that has an x to the power 4 of the form 4, okay, to the power 4, 3, 2, okay. Of 4th degree. Quartic phase gate. So another small tangent, higher order gate decomposition. Now we are probably thinking, hold on one second, how are we supposed to deal with exponentials of this? Well, never fear, we actually have a method to decompose this gate exactly using the research presented by Kalajewski and Arrazola in the paper Exact Gate Decompositions for Photonic Quantum Computing. See references for a link to the paper. The paper is genius. If you're interested, I highly recommend at least quickly going through it, but we can essentially decompose our quartic gate into a product of a bunch of lower order gates. I'm not going to go through the proofs calculations, but for even n, the paper rises to the following relation. Okay. I guess the paper is highly mathematical, so it's probably not going to be interesting for me, but okay, that's the idea. Yeah, but that's... there's not much intuition that I can see in here. So for the case of n4, we get the following. Paper also gives us an identity. Okay. So we have a method to implement gates of this form as well as gates of this form. All we have to do is use a couple Fourier gates. I know it's a bit of a mess, but we'll break it down and implement it into our simulation into chunks. We can start by creating a function that generates a specific gate. Crazy gate. Oh my god. V gate, R gate, V gate, R gate, control Z gate, R gate. Boy. Is it a coincidence that there are 4 control Zs? Oh, because it's the repetition of the same. Okay, sorry. So it's this repeated 4 times, right? VR, VR is CZ. No. No. Different things. So there are 4 control Zs. Here, 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 and here. Quartic gate. Oh my god, that's in here. Crazy gate, okay. Yeah, that's crazy. Okay, that went too far, too fast, definitely. Excellent, so we can implement our simulation one more time. As usual, we first have to define our value of Planck's constant as well as the classical cost function, which will given by this, and define our cost and mix as unitaries. Quartic gate, P gate, quartic gate. I guess that was supposed to be crazy gate, right? I know that's quartic gate. That's quartic gate here. Yeah, go blank for a second. So cost ham, mix ham, price our numerical circuit simulator. Now here's where things get interesting. I promise this is our last detour. Numerically calculated the cost and expectation value. The next step of research should be to define our objective function, which we'll minimize. Usually we would do this through finite sampling, but in this case we will try something new. Our cost Hamiltonian is of the form this, that, this, those. One key determinants for each iteration we want to find for the prepared state vector S. Usually we would have to sample the circuit repeatedly to obtain this expectation value. However, we are going to be sneaky for this simulation because sampling a circuit this deep will take a nightmarishly long time. Not really, but I'm super impatient. We have these. Okay, so this tells us something very useful. Essentially, we already know this is just the x quadrature probability values. We also already know how to integrate over it numerically. This while we take this integral, we simply have multiply either this or that inside the integrand and then put the. This technically is cheating, but we're just experimenting, so I'm going to accept this as allowed. As you can see, we're on numerical simulator 1, so integrate again. This is one confusing technique is divided by 0. What's the data before we calculate the expectation, but let's find out as we define our parameter. And basically, visualization. Pretty good actually, if that is the function. So we get pretty great results with two spikes appearing at the minima of the cost function. This simulation, however, required a very deep circuit, depth of 8, so there is definitely a trade-off that must be considered between accuracy of the algorithms and depth of the circuit, which on a real quantum computer would lead to loss of coherence. Conclusion. Okay, so we got at the end. I thought it was longer, but I mean, I went fairly quickly through all that, and I definitely let me then pause for a second and try to sink in that for a while. Conclusion is novel was meant to act as expository material to give the reader an idea of what QAOA and CVQA are all about through some interesting physical theory in the first section, concrete simulations, gain more clarity about the power of this algorithm. To address this inaccuracy of the simulation, a lot of these results kind of got lucky when I ran tests locally. I got a lot of great results, but at the same time I got a lot of not so great results. I also feel as though I am selecting ideal parameters for each of the simulations, as a lot of the squeezing parameters, cut off dimensions, etc. that I tested, which I didn't include in the notebook, did not work very well. Nevertheless, I think this is an interesting starting point to dive farther into CVQA and conceptualize better training techniques in more general ways to choose parameters such as conversions of the algorithm can be ensured to a higher degree. Acknowledgements, of course, after completed without the help of Guillaume Verdon, Josh, Isaac, Nicolas Quesada, Juan Miguel Arrazola, and Nathan Killeran. Thank you to all of you guys. I really appreciate that you took the time to answer my never-ending stream of questions. Okay, so here's the original paper. That's the CVK decomposition one. How does it look like? The code of the contour graph was based off a stack exchange answer. We'll update with lane Gaussian. That's cheating. Propose a method for decomposing conditional conversion to universal gate set without use of any approximations for the meaning exact percentage current percentage. 11 pages. Okay. Exact decomposition. Yeah, whatever. That's too technical. So where do we go from now? Back to his blog post is definitely next step, and then diving into some of the material from Guillaume, I think that will be probably next video, and then back to Mihao. Yeah, then back to Mihao, and I kind of then think I would have spent a relatively comfortable amount of time on this subject. I'm definitely far from really being able to from I'm let's put it this way, I'm quite sure I'm just at the surface, scratching the surface on this. But I want to kind of close those things up and then see if I organically come back to that topic later on through other papers, I think. But there's a lot of material from Guillaume as well that I'd like to review, so I don't know if I'm going to spend too much more time on this in general. But let me recap for a second. So really, let me try to kind of ultra summarize that at an intuitive level. I mean, basically, there's this bit of introduction in here, sort of the theory, right? Yeah. There is this bit of so I'm trying to find out a customer's rate looks like something like this. This is the bit that I think it's in Guillaume's paper somehow with CVQA. We follow this general process of a discrete version, which is a constant mixer Hamiltonian, which we then trottleize and recursively act upon our photonic modes. For each step of the algorithm, we write the unitary as this and this and this and this. So our mixer, we are required to yeah. So, okay, but anyway, there's a bit of theory, as I said. Sorry, let's just stay here. Background theory. Then you've got the simple problem with approximating, trying to optimize. It's a function with one input variable. Then there's another function with two input variables, and the interesting part here intuitively is that there is this control Z gate appearing here, because I guess that's natively that's unavoidable, because you're basically by design modeling something that has a relationship in it, so those things are not totally independent. Then you've got sort of 4, 5, and 6. It's more like, how can we take it one step farther and go for a function that has a power to the 4, sort of a 4 degree. I don't know how it's called, but a function like a polynomial function with like an exponent of like something, one variable to the power of 4. But the gist of it is that basically builds on top of another paper that explains how to break that down into lower degree functions, and then just going through the previous examples. And I think Jack has to do a bit of a workaround here to get the expectation value, because the circuit is too big. And so what he does is he integrates. But what is he integrating? state vector is that we would like to have a sample circuit repeatedly to obtain the expectation value. However, we're going to be sneaky for the simulation because sampling a circuit is long. So he's basically pulling that off here for some reason. I know he's pulling that off. No, I want to know, I think. And then this is something that we, can do here. That's what it's kind of compacted in the new objective function, I guess. You should also notice that we normalize our data points if we're integrating. Yeah, but I mean, really, the one thing that I take out of this video is the control Z thing. I like it. The fact that I'm still missing sort of the intuition, like a better picture intuitively how to build those. It maybe doesn't make any sense, you know. Maybe this is something that, you know, if you wanna get precise and you need to go, you wanna get down to the mathematical description of things, because at the end of the day, that's what gates are. The gates are just pure physical, I would say, processes or actions that you apply to your mode, to your actual physical modes, and you know, they basically are described mathematically, like they have a mathematical transformation, like a geometrical or mathematical transformation behind it. And so if you have a concrete recipe of something you want to implement, and then you've got your recipe that you want to implement, and then you've got your set of gates, then you know you gotta find that mapping, right? And you're gonna do that mathematically. So in this case I don't see it so bad, because that it's sort of the way this is introduced already forces you to think this way, because it's like, oh yeah, the premise is, you know, we know that in QAOA we just do it this way, and you know, you've got your cost function and your matrix. It's fairly late and I'm a bit tired. That's when I start saying weird things. What I was gonna say. This here. This oh yes, this here. This is basically similar to pronunciators that we use for QAOA. Sorry. This is actually what I meant. Yeah. The integers that we use for QA. So QAOA kind of imposes you these, or at least that's the way they put it in continuous variable quantum computing. Because in discrete variable quantum computing, there seems to be a connection. There seems to be a structural connection between, or at least, you know, the VQE read the docs from Circ. There is a sort of a mapping between the way you model the problem, right? Because I was, you know, constructing that circuit. I was going through that, and then, you know, reasoning. You can check out the video, and it's like, with the isotopes, whatever, the Ising model, exactly, the Ising model, and we're basically mapping that model into a quantum circuit, and that was the ansatz. But here, CVQA, it just tells you, you know, that's how it should look like mathematically. Maybe that's what I'm missing. Maybe that's. So I think what I will do, because I want to clarify this, I want to see where that comes from. If that comes from the paper, Guillaume's paper or not. Guillaume's shared in Twitter that he's got some some material at the intuition level. That he's got some slides, I think, or something in the paper where it explains that intuitively. So I'm gonna do that. I'm gonna do that as part of the next video, and we'll see. We'll take it from there. See if we, I'm trying to push hard. I'm trying to rush it a little bit, but I'm trying to push to go back to Michał's video, Michał's the Yellow Submarine project, and at some point go back to or take a look at the paper that presents that neural network architecture that the Yellow Submarine project is reusing, and then we're gonna close this whole thing. Yes, and eventually go back to discrete variable quantum computing. I guess it's gonna be a back and forth, and I don't know if ion traps have a different model behind it as well. So I'm also wanna explore that. I mean, there's so much that you can take out of all those different models that kind of help you learn, especially if you understand sort of the analogies and how some things connect to each other, and beam splitting as a way to create entanglement. The squeeze gate being an analog of the Hadamard gate to some extent. Yeah. So, but that's basically the summary of the notebook, without really going into super deep technical details. It's like the simple problem, the harder problem, the extremely harsh problem, but the explanations given in the notebook are rather on the mathematical side rather than the intuitive side, and that's still what I'm kind of in the middle of, what I'm kind of researching, so to say. But cool stuff.